So all you guys sitting on this side will make it a little bit easier for me today because I can just look out here and I don't have to keep going back and forth. So let's go where we left off last class. I introduced this idea of Bayes' theorem. Right? So the setup for these examples are always going to be that we have two states of nature. All right? Those are the only two states. Okay? So we think about examples of this, someone's either guilty or they're not, right? That's just, they either are or they're not. Not what a jury finds them, but like if they're the actual state of nature. They are either committed the crime or they didn't. They either have a disease or they don't. They're either pregnant or they're not. We can kind of think of all these examples where there's only two outcomes. Well, if there's only two outcomes, the probabilities of those two outcomes or those two states of nature would then have to add up to one. Okay? So we want to know what the underlying state of nature is. Like, I want to know if someone's guilty or not guilty. I want to know if they have the disease or not. But I can't just look at them and know. I actually have to perform some test, right? So I then call E and E complement the two results of the test, okay? So we're going to throw out the idea of, something that's like inconclusive. We'll say, this test, we run it until we get an answer, right? So these test results would be positive or negative, guilty or not guilty, right? We're trying to look at what the true state of nature is, but all we can observe is the outcome of this test, right? So the test we usually think about as like positive or negative, right? Positive or not positive. So what we're thinking about is then we observe the outcome of this test. So maybe we see that it comes back positive. Given that the test comes back positive, what's the probability that the true state of nature is the person actually has the disease, right? Because I know that, there are some false positive tests, the test is 100% accurate. And so I might want to try to find this conditional probability, which we think of as, given that someone has a disease or given that they, test positive for HIV, given that we see the outcome of the test be that they test positive, what's the probability that they actually have the disease? Okay. So that's something like we might want to find. Well, using what we've done in the past, you might think about take that conditional probability and just rewrite it as the intersection divided by whatever we're conditioning on, right? But if we think about even just as simple as what this denominator represents, what's the probability of seeing the outcome E? So what's the probability that we see a positive test result? Well, I don't know the probability that if I administered it at random that I get a positive test result, right? That's going to depend on if the person has a disease or if they don't, right? How many people don't have the disease versus how many people that do. And so it's not going to be very common that we just are given this probability that we get a positive test result back from some random person in our population, right? We probably have information on what are false positive rates, what percent of people usually have the disease, what's a false negative rate. But we're not given directly just what's the probability the test comes back positive, given no other information about the person, right? We know that the probability it comes back positive varies whether or not you have the disease or not. So we're going to use this definition that we know we can also rewrite the intersection of something as the conditional probability times what we're conditioning on. So we're going to rewrite the numerator up here as a conditional probability times what we're conditioning on, plug that into our numerator. Now the denominator we can break down, so the probability we see a positive test result is going to be composed of two different types of people. The first is someone who sees a positive test result and actually does have the disease. The second is the probability someone has a positive test result and they actually don't have the disease, right? Or state of nature 2 is the true state of nature. So I'm going to have some people, right, who have the disease and see a positive test result, and some people who don't have the disease but still saw a positive test result. So if I add those people together, that should just give me everyone who has a positive test result. Right? I can then rewrite these intersections as conditional probabilities times what I'm conditioning on. Notice I'll be conditioning on the different states of nature because here this was S2 and this was S1. I'm just rewriting my intersections here using that multiplication rule. I then can plug this into my denominator. I try to color code this where I'm plugging things in. And basically I rewrite this as a longer equation. Now, like I said, why am I doing that? Because I'm never usually given directly these probabilities. But I likely will have information, some conditional probabilities down here in this setup where we have two states of natures and two outcomes of the test. Okay? I'll work through some examples, and I think it'll be a little bit more clear why we had to break things down to this level. Now, I'm not ever going to ask you to reproduce this or like show me how we go from this to this. But I'm just kind of showing you the behind the scenes how we get here. Okay. So now that we have this general form of the equation, we can start to think about answering some questions that we talked about earlier, right? The probability that someone has the disease given that I saw a positive test result. So, oh, sorry, I forgot. There's one more thing I want to mention before we go into the first example. Forgot about this slide. So we already talked about this, right? If there's only two states of nature, the probabilities of those two outcomes should add up to 1, right? If the probability that somebody has, COVID is 0.1%, sorry, is 10%, so probability of 0.1. The probability that they don't have it would be 0.9, right? There's only, they either have it or they don't. So those two things add up to 1. What's a little bit different is if we condition on the same state of nature, right? So let's say I'm in this room of people and I then say, okay, only the people who, don't have COVID stay in the room, right? So everybody else leaves. So I'm conditioning on the same thing, right? Well, maybe now I have 100 people left and 10 of them end up with a positive test result and 90 of them end up with a negative result. That's the only two things they can end up with, right? Well, then given that I'm looking just at people without the disease, the probability they saw a positive test result would be 10 out of the 100 or 0.1. The probability they saw a negative result would be 90 out of the 100 or 0.9, right? So those two things have to add up to 1. If I'm conditioning on the same state of nature, it's almost just like we went from this larger group and then we just cut everybody else. So now our new group is whatever we've conditioned on, right? And of that group, they either get a positive result or they get a negative result, right? They see one of those two outcomes of the test. So if we condition on the same state of nature here, and the reason why I wrote a SI is because it could be that you condition on state of nature 1 for both of these, or it would also hold if you condition on the same state of nature S2 for both of these, right? You can only see those, once you've conditioned on the same thing, there's only two outcomes of the test, so these two conditional probabilities have to add up to 1. Now, if you start conditioning on different states of nature and looking at outcomes of the test, all bets are off. That could be anything. In fact, if you did something goofy like this, you could end up having a probability over 1, right? Which doesn't make any sense because this doesn't, if we're conditioning on different states of nature, this just doesn't really mean anything to us, okay? So we have to make sure we condition on the same state of nature here. So let's go to a HIV test example. So I'm gonna try, first I'm gonna have to go out here and switch my camera over. There we go. I'm gonna go share my screen and blow this up as big as I can. So if you're on Zoom, I'm gonna be having the slides pulled up and kind of a video on the screen as well. So make sure if you usually just look at the screen share, pull up that little tab where you can see my video and kind of open it up large. That's what the recorded video will look like, and that's what you guys in class are going to see. So I'm going to try to write this big. If it's too small, make sure you ask me to clarify. But let's say the probability that if I chose an American at random today, that they have HIV is about 0.006. Right? You can go out and Google, that's about what it is. Right? I tried to make these real. So the probability that if I just choose someone at random, that they're HIV positive is 0.006. Now, one of the rules I said I know is that the probabilities of the two states of nature, we'll call this S1, have to add up to 1, right? So what would my other state of nature be here? So you're right with the probability. What am I looking for? Yeah. You jump the gun a little bit, right? So the other state of nature would be that they're HIV negative, right? Those are the only two things I could see. Well, if these are my two outcomes, we know these have to add up to 1. So subtract this from 1 and we would get that 0.994, right? And I'm kind of writing this here, think about these are adding up to 1. That's what I was trying to indicate with that, okay? Now the next thing we're given here is the probability an HIV test comes back positive for a person who actually is HIV positive is 0.999. So these are really good tests at identifying it if you have the disease. Or said differently, given that somebody is HIV positive, the probability that we get a positive test result, I'll just write this POS.test, we were just told was 0.999. Well, notice, if this is my state of nature 1, and this is my outcome of the test E, if I condition on that same state of nature that the person is HIV positive, but I want to know what's the probability that they get a negative test result, or E complement, what should that be? Well, remember, when we condition on the same thing, it's like I kicked everybody out of the room that was HIV negative. I only am left with people who are HIV positive, and I tell you the probability of those people that they get a positive test result, 0.999. So the probability they saw a negative test result would just be, right? We're conditioning on the same state of nature. These two things should add up to 1. Okay? Any questions on that before we keep moving? I'm going to pull the chat open, so if I do pull it up, we'll go up here. We're okay with that? All right. And then the last thing I'm given is the probability that we see a positive test result for a person who's HIV negative is 0.01. So now what we're saying there is, given that someone is HIV negative, this is our S2, right? The probability that we see a positive test result is 0.01, or think about it, these are like our false positives. So if I condition on that same state of nature, S2, what's the probability I see the other test result, or a negative test result? Once again, it's like I kicked everybody out of the room with HIV. Now I'm only looking at people who are HIV negative. The probability they get a positive test result is 0.01. So the probability they get a negative test result would just be, right, whatever gets us up to 1, because we're conditioning on the same state of nature and looking at the two outcomes of the test here. Okay? Any questions on any of that? So that should give us all the probabilities we would ever need. If you're working through a Bayes' theorem example, even if you're not, we're only directly given 3 of these, right? We actually had to figure out what these 3 were, right? So in a Bayes' theorem example, you can find 6 probabilities. You don't necessarily always need them. We're actually going to work through this problem, and we would have seen that we actually didn't need to do some of this work. But no matter what question I asked you, this would give you all the information you would need to be able to answer any question. Okay? So the next thing we're going to look at is if the test was administered. Sorry, is everybody okay with it? Can I move this? Okay. So if I administer a test at random and it comes back positive, right? So I give somebody a test I chose at random and I see a positive test result. What's the probability that the person actually has the disease, right? Hopefully this is high, right? But we'll actually see, we can compute this, right? So I've got my state of nature here and my outcome of the test, okay? So what I'm going to do, and I'll walk through the next example a little bit more in detail. I'll kind of gloss over this a little bit just to kind of have it set up. So what I'm going to do is I'll go back and I'll look at this general form of the equation, okay? My S1 is being HIV positive. My E is seeing a positive test result. I'm just going to write this equation out in the context of my example. So everywhere I see an S1, I'll write HIV positive. Everywhere I see E, I'll write I see a positive test result. Everywhere I see S2, I'll write what? If S1 is HIV positive, HIV negative. And I'll just write that out. We'll skip this slide for a second. In the context of my example, right? We identified what we were looking for. We had all of these probabilities that we had calculated. We wrote it out in the context of our example. Now it's just a matter of plugging in our values. What's the probability someone's HIV positive? 0.006. Given they're positive, what's the probability to see a positive test result? 0.999. 0.006, 0.999. You'll notice, and I'll explain why intuitively in a second, the first part of your denominator is always the same as the numerator. Okay? Probability they're HIV negative, 0.994. Given that it's negative, the probability of a positive test result, 0.01. Now I showed you how to find all the other information because I could have asked you something different where you would need those, and you'll see an example of that here in just a second. But really here, I had everything I needed to just plug in all those values, and I actually end up with a probability here of 0.38. So given that I see someone have a positive test result, the probability they actually are HIV positive is only, what, 38%? Now, why is this so low? I mean, I shouldn't say it's low, but we would hope it's higher, right? You know, people getting positive test results think they've got this disease. So what's going on here? So anytime we have probabilities, we talked about this last class, we built contingency tables. We first calculated what before we got probabilities? We first had to find the frequencies, right? We were using that count ifs to find the frequencies. And then we divide everything by the total number of observations. Well, if everything's divided by the same thing, intuitively, we can think of probabilities as frequencies, and it's still a correct way of thinking about it. So let's use these probabilities and think about what the numbers would be like. Right? So what I was really saying there earlier is what, 0.006%, or sorry, 0.006 was the probability. 0.6% of Americans have HIV currently. I'm going to really roughly estimate some numbers here and round pretty egregiously just to get the numbers to work out nice, but you'll see it doesn't affect us too much. So let's say instead of 0.06, we just use 0.005, so 0.5%. And let's say we say America is about 300 million people. Just makes the math a little easier, okay? So 1% of 300 million would be 3 million, 0.5% would then be, we've got 1.5 million people who, if we were to administer a test to everybody, would be HIV positive and, think about and here, see a positive test result, right? Because there were 1.5 million people with the disease, and the test correctly identified them 99.9% of the time. So I guess theoretically, this is going to be like 1.499 million or something, but we'll, roughly 1.5 million. Then we've got 99.5% of people that don't have the disease, right? So about 300 million people don't have HIV. But the false positive rate was 1%. So if all of them take a test, right, 1% of them would actually come back and have a positive test result, right? So we would actually have about 3 million people, just shy of 3 million, who don't have HIV and end up seeing a positive test result. So I've basically got, if I could give the test to every single person in the US, I'd see about 4.5 million people with a positive test result, right? So I've got about 4.5 million people with that positive test result, but what's the probability if I were to choose any one of them that they actually have the disease? Well, there was only 1.5 million people who actually had it, and so this is roughly, 33%. I rounded a lot here. If we actually worked through the numbers, we ended up, if we just used the probabilities and didn't think about frequencies, we ended up at 38%. So, I mean, it's a little off because of my rounding, but that's the general idea, okay? And really what you're thinking about here is what was in this denominator? Well, it was, was that off the screen? Sorry. It was 1.5 million. How did I get that 4.5 million? I just added up the two different types of people I could see. Those who had a positive test result and had the disease, those who had a positive test result and didn't. Notice that's really what we're doing with probabilities. Remember I said the first part of the denominator is always the same as the numerator, right? And that's why we're really thinking about, out of the people that get a positive test result, what proportion of them actually would have the disease, okay? So you can think about these as frequencies, and I think sometimes that makes it click a little bit better, okay? Any questions on this before we keep moving? Okay with this? All right, so I'll go back here, skip something. So I used to like teaching this a lot more. And I don't know, I feel like people don't use it or they don't like it as much. And the way that I actually showed you already is kind of preferred. But some people like to think about, when we're finding those probabilities that weren't directly given to us, think about building this tree, right? So you've got originally, what are your two states of nature? You could either see someone be HIV positive or they're HIV negative. I was only given this one, but I know this like row of the tree, the two states of nature, have to add up to 1. So once I knew this was 0.006, I automatically knew this was 0.994. Then on this branch of the tree, I'll condition on that state of nature, right? So I'm conditioning on that someone's HIV positive, and then the two probabilities I'm looking for, the conditional probabilities, will be the two different outcomes of the test, right? Well, because I've conditioned on the same state of nature, I know these two probabilities will add up to 1. So when I'm given only one of them, I can automatically find the other. And then over here on this branch, I condition on whatever state of nature this branch has, right, being HIV negative. But the probabilities I'm looking for are the two outcomes of the test. And then I would know these probabilities that on this rung of the branch have to add up to 1 as well. So some people like the tree as a visual. Some people simply like, right, doing it this way, where you can kind of see if I'm writing these out, they kind of get grouped and they add up to 1. It's really just personal preference. Where else did I want to say something here? I think we were good through this. Are there any questions on this before I move on to the next example? I think we covered everything I wanted to say there. So let's say instead, we've got, this is going to be kind of a goofy example, but I'm going to try to connect it with something at the end, so bear with me. Well, let's say I'm tired of our criminal justice system. I think juries get it wrong way too many times. And some scientists have created some truth serum that makes people either confess to a crime or not, right? And hopefully it's accurate, right? So, I go to the scientists and they tell me, if someone is actually in fact innocent, the true state of nature is they're innocent, this truth serum will accidentally make them say they're guilty 1% of the time. So it's pretty, not very, it's not terrible rate, and it's not too high. But given that someone's guilty, it won't force them to say they're guilty, right? They'll actually still say they're innocent about 10% of the time. Okay? So this is the information I'm given, these two conditional probabilities. I'm then told, if 5% of all suspects who are given the truth serum are guilty, right? So the underlying probability of the state of nature, the probability someone's guilty is 5%. So what would be the probability that they're innocent? 95%, right? Or a probability of 0.95, right? Those are my two states of nature. Those probabilities have to add up to 1. So if the truth serum indicates that they're guilty, what's the probability that they're actually innocent? Okay? So what we're looking for here, right? We'll first identify what we're looking for. Okay? So the probability that, given that this truth serum makes them say they're, was it guilty? Yeah, truth serum makes them say they're guilty. What's the probability they're actually innocent? I'm just going to shorthand innocent and guilty with ing. I did in last class and I ran out of the room a lot, so we're going to try it this way. What are we given, right? Well, we know that the probability someone's guilty was 0.05, and we said the probability that they're innocent was 0.95. And then we were given these two probabilities here, these two conditional probabilities, right? So that's the setup here, right? We've defined what we're looking for. We've identified the 4 probabilities that we have, and we can figure out some other ones here, which we're going to have to in a second. But for now, this is directly given to us. We're going to write the formula out in the context of our example. So I'm going to walk through how we do this instead of just showing it to you. So I'm going to go back to this slide and use the general form of this equation, but write this out in the context of my example. So here, this was my outcome of the test. The test was this truth serum. And my state of nature was that someone was innocent, right? So I'm going to write out Bayes' equation, but in the context of my example. So my S1 is that someone's innocent, right? So I'll write in the probability someone's innocent times the probability of E given S1. Well, my E is that the truth serum makes them say they're guilty, given my S1, which is that they're actually innocent, right? So I just wrote out that numerator in the context of my example. I think I mentioned this already, but notice the first part of that denominator is the same as the numerator, right? So I can just write that out pretty easily as well, right? It's the exact same thing that I just had written above. Okay, What's my S2? My first state of nature is being innocent. S2 would be that I'm guilty. So probability that they're guilty times the probability of E given S2. Well, my E was that the truth serum makes them say they're guilty, given that S2, which is that they actually are guilty. Right? Now that I have this written out in the context of my example, it's just a matter of plugging in my values, right? So I want to kind of walk through and show you how you would go through that process. But it's really just looking at this equation, identifying what you're looking for, what your state of nature, what your outcome is, and writing this out in the context of your example. Okay? All right, I'll leave this up here and I'll scroll through the slides. Go back to our example. So we stopped off here. We wrote that formula out, right? This is what I had up on the screen there. Just start plugging things in, right? The probability they're innocent, 0.95. Given they're innocent, true serum makes them say they're guilty, 0.01. Probably they're guilty, 0.05. But I don't have this, right? I'm missing this probability. So I plug in all my values, but given that someone's guilty, I don't have the probability that the true serum makes them say they're guilty. However, if I would have done this like I had the HIV problem, I would have identified all those points already, or I would have built the tree and said, if I condition on the same state of nature, so given that someone's guilty here, I know the probability the true serum makes them say they're innocent is 0.1, so the probability it makes them say they're guilty should be what? Condition on the same state of nature, 2 outcomes of the test, they should add up to 1, so if one of them is 0.1, the other one is 1 minus that, or is 0.9, right? Whatever gets us up to 1. Right? So I then plug the 0.9 in there, and now I'm done. Right now, it's just kind of simply making sure I can get this entered into my calculator, okay? Okay. Any questions on that, or are we okay with that? Okay. Yeah, plug and chug. Just plug that into your calculator at that point, right? All right. So if we actually do this, we get about 0.17, right? So given that the true serum makes them say they're guilty, 17% of people are actually innocent. You know, if we see that someone confessed after this true serum, 17% would still be innocent. So this may seem like kind of a dumb example, but let's just, well, I'll skip this slide for a second. Let's just replace true serum with jury, right? And it's the exact same thing. We could actually find these probabilities. So given that someone's guilty, the probability a jury actually found them innocent, we can get an idea about what that probability is by going back to certain time periods and looking at cases that have gotten where they went back and found DNA evidence and then later convicted a person that was, right? Because at the time they didn't have certain, technology advancement, they didn't have DNA evidence. And so we can get an idea about how incorrect juries were in like a certain time period to maybe figure out what this probability is, right? We could do the same thing like with innocent project stuff where given that someone's innocent, it's got a beard hair in my mouth. What's the probability that juries found them guilty at that time? So we can get an idea about what these probabilities are from looking at historical data and overturned cases. And then it's just a matter of writing everything out. Instead of truth serum, we've just got jury here, right? And we could actually find currently, based off of that data, what's the probability that if someone's in prison right now, a jury found them guilty, what's the probability they're actually innocent, right? So we've got, the people who are guilty and found innocent, people who are innocent and found guilty, right? Not arguing one way or the other. These are just cultural references. But, hopefully it's not as high as 17%, right? Right. These numbers, I just kind of made them up to make some sense, but I don't know what the exact numbers are if we looked at overturned court cases. But it's a direct application of what we're doing here. You could do that. Okay. So we found, given that the true serum makes them say they're guilty, the probability they're actually innocent is 17% of the time, or a probability of 0.17. So what if I had the exact same setup, but I asked you for what's the probability that if a true serum makes them say they're guilty, what's the probability that they are actually guilty? So you could go through this whole thing, write out Bayes' theorem in the context of your example again, plug in all the values, and figure out what that is. But notice, if what I just found was that given that the true serum makes them say they're guilty, the probability they're actually innocent was, I think was it 0.174, right? Well, now what I'm looking for is that given the truth serum makes them say they're guilty, what's the probability that they're actually guilty? Now, it's a little bit different than something I told you earlier, but very similar in the way it works. If I'm thinking about, I'm conditioning on the same outcome of the test here, what I've really done is said, okay, let's say I started with a room of a ton of people, and then I gave them all the truth serum, and I only kept the people that the truth serum made them say they're guilty. So maybe now I'm left with 100 people, right? Excuse me. The probability that if I selected someone at random out of that group that they're innocent is 0.174, which means the probability if I selected someone at random out of that group, the probability they're guilty would actually just be 1 minus that, right? Because given that I'm looking at people who confess to the crime, they're either innocent or they're guilty. I'm looking at the same people. I'm conditioning on the same thing. So this would just be what, 0.826, right? So similar to when we condition on the same state of nature and looked at two different outcomes of the test, if I condition on the same outcome of the test, but look at the two different conditional probabilities of the two different states of nature, excuse me, those should add up to 1 as well. So it saves me a little bit of work, right? I didn't need to necessarily know this, but because I could have used this, wrote out my Bayes equation, plugged everything in. But hell, if I had already done this work, this saves me a lot of time knowing this, right? And I think with these, it's a matter of like stopping and thinking about what these probabilities are looking at. Because if I just look here, I might, okay, are these on the same side? Or no, think about when you condition on something, it's like I'm only looking at people for which this is true. The probability, if I selected out of a room of people that this is true for, 17.4% of them are innocent, which would mean 82.6% of them have to be guilty, right? Or the probabilities here kind of moving that decimal. Okay? All right. So I wanted to point that out because we can save ourselves a little bit of time there. We already talked through this. I'm actually going to do something a little different. Oh, I thought I had it open. Is it on my PDF? Yeah. So I don't know. Trying to make this like very relevant to the times right now and give you another example of some Bayes theorem stuff. No, this might be a little bit alarming. I was trying to find the best source, and I think this came from like Lancet, but there's some citations of where is it? So like Imperial College in London. So there's other resources I could have used, but this had both the rates in the same article, so I just grabbed that. So if we look at false negative rates for COVID tests, if we looked at all the data, they range from 2 to 33%. I'm going to use the best case scenario of 2%, right? I looked at a couple other papers, and I didn't see things as high as 33. A lot of them were saying like between 2 and 4 or 2 and 6. So we'll use the lowest of those studies, which found that it was a 2% false negative rate. They also found that false positives are somewhere between 0.8 and 4%, right? So here, I'm going to use, let's use a pretty low estimate of that, and let's just use like, well, we'll split the difference on this one because I think the other resources I looked at, all of them kind of have the middle point is always around 2%. So let's say our false negatives and our false positive rates are both around 2% based off of kind of some of the studies that have been out there. Okay? If you look at, if you go out and search like COVID new cases, in the US, right, we're thinking about US here, it's approximately like 100,000 a day in the last 14 days. If we look at this, like 7-day averages. So if you think that like, at any one point in time, we'll use a 14-day time period because people could last for 14 days. That would be 100,000 times 14, about 1.4 million. We'll say it's about 1.5 million people. We think about the US being 300 million. We'll even be generous and say at any one point in time, about 0.5% of people have COVID in the US. The cumulative total is like, I think getting close to 20 or something, or between 15 and 20, I think. But at any one point in time, about 0.5% of people in the US have COVID currently. So really what we're thinking about there is the probability that someone, if I just selected somebody at random today in the US, the probability they have COVID is about 0.005, right? Which means the probability if I selected someone at random that they're they have a negative test result would be what? It's the other state of nature. So those two states of nature have to add up to 1, right? So 0.995. All right, I was then told the false negative rates are 2%. So a false negative would be that given someone actually has COVID, the probability that they see a negative test result, right, or a false negative was about 0.02. And this was the one that could be even a little bit higher, but we were going to use kind of the lower level estimate of it. We were also told, given that someone is COVID negative, the probability that we get a false positive, right, they're negative, but we get a positive test result, was also about 0.002. Now this will help us when we're plugging values because we could make a mistake, but we have similar values here. But given this information, I then could be interested in, well, look, if I go out today, I feel fine, you know, we're also kind of ignoring a little bit in this that, you know, people showing symptoms, these rates might change. But if we were just to administer a test to everybody, if we had that capability today, that's a scenario we're thinking about. If I see a positive test result, what's the probability that I actually have COVID? It seems like a pretty, you know, common sense or something that I might be interested in, right? I go out, I feel fine, maybe I'm asymptomatic, but I get a positive test result. Well, do I actually have COVID? I mean, you could probably look, that'll be probably a pretty highly Google search term, right? So what we're going to do is write this out in the context of our example, right? So we've got our state of nature and our outcome of the test. So if we go back, and we were to go back to our slides, using this general form of the equation, all I'm going to do is write this out in the context of my example. Okay? So I've got my S1 and my outcome of the test E. If I can get this. So I'm just going to start writing this out in the context of our example. So our S1 is what? Probability that they're COVID positive times the probability of E given S1, so that we see a positive test result given they're COVID positive, divided by, and here I'm not going to rewrite it because it's the exact same thing. We said the first part of that denominator is just the exact same thing we have in the numerator. Right? But just for the sake of giving myself a little more room. Add in the probability of S2. So what would S2 be here? If S1 is that they're COVID positive, S2 is that they're, COVID negative, times the probability of E, so seeing a positive test result, given S2, or given that they're COVID negative. Right? And now it's just a matter of plugging in my values, right? What's the probability someone was COVID positive? We go back up here, 0.005. So 0.005 times, given that they're COVID positive, what's the probability they actually see a positive test result? If I look at my original data here, I actually don't have that, right? But conditioned on the same state of nature, I know the probability that if someone has COVID, the probability they see a negative test result or a false negative is 0.02. So the probability they see a positive test result here should be what? Yeah, right? It's like I'm looking at people with COVID who are COVID positive. There's a 2% chance they get a negative result, which means there has to be a 98% chance they get a positive test result. Right? So we'll plug in down here, 0.98. We then said we have the exact same thing as the numerator as the first part of our denominator. What's the probability that someone's COVID negative? We go up here, we said that would have been 0.995 times the probability that, given that they're COVID negative, what's the probability to see a positive test result? Well, we actually were given the false positive rate. So this was 0.02. Oops, 0.02. Okay. So I wrote that out in the context of my example, and then kind of plugged in my values. Right? So what is, if I see a positive test result, what's the probability I actually have COVID? Everybody okay with this? I switch off of this, still writing. So I'm pretty bad about using calculators. I don't like to. I don't usually have them with me. So let's use Excel as a calculator instead. So we had 0.005 times 0.98 divided by 0.005 times 0.98 plus 0.995 times 0.02. Right? So we can think about really what this represents is, well, these were the people that didn't have COVID but got a false positive rate. Here's the people who did have COVID and were correctly identified. So like that's my total group of people that got a positive test result. Out of those people, the numerator here represented the people who had COVID and got a positive test result. So this is like the proportion of people who get a positive test result who actually have COVID, right? So we go ahead and compute that. It's only about 20% given those rates, right? So if we made every single person go out and get a COVID test today, the issue with that, right, is that, yeah, the false positive rate isn't high, it's 2%. But most people at any one point in time, I'll switch over, right? Most people don't have COVID, right, at any given point in time. So if I made everyone go out and COVID test today, yeah, 2% of isn't a high percent, but 2% of nearly 300 million people is going to be a lot of positive test results, right? So yeah, it's good to get people tested, but to just get anyone tested, right, if we know that the false positive rate is relatively high, it's somewhat dangerous because it then means the positive test result has a lot less, like it gives us a lot less information. It's not near as valuable, right? I mean, the fact that, it's only 20%, well then, getting a positive test result means nothing. Most people are going to look at that and say, well, I got a positive test result, but who cares? It's a 4 in 5 chance I don't have it, right? If we made every single person go out and get a test today, right? This is not saying that you should ignore a positive test result currently because we know the percent of people that are getting an actual COVID test, much higher percent of them actually have, right? They're going there because they have symptoms, right? So it's not this 0.005 versus 0.995, right? Because not every single person's getting a test. So it's a little bit different, but this does highlight the problem of if we mandated, every single person get a test today, right? That's going to, make that test result a lot less useful, unless we do things like, run multiple tests and things like that. Then the story changes. But yeah, this is so Bayesian theorem is kind of interesting because it kind of goes against your intuition, right? If we really did these tests for disease on a mass scale, the test result isn't going to be really that reliable, just if that's all the information you have about the person, right? Now, the more conclusive test gets, and the smaller that false negative or that false positive rate gets, well, yeah, then it is very useful. So if we're thinking about, testing for most diseases, it has, they've perfected over a long period of time, it becomes a little bit better. Even just notice the difference between this and an HIV, right? The HIV rate probability we had was, twice as high, right? Twice as kind of useful to have that positive test result. And, I'm sure over time, hopefully this will improve as well as those tests get better. So. Any questions over any of that? We'll save some of this stuff for next week. So just some fun, interesting examples that I think I'll save until next class, maybe a more boring class. I kind of like talking about these Bayes theorem examples. They're pretty applicable. Don't forget your Connect and Excel assignment are due by the end of the day today. So for the Excel, you're uploading kind of those files to Canvas. Other than that, I think that should cover everything. Any questions from me before you guys get going? All right, yeah, I'll see you guys on Monday.